Okay, so this is about conservative explicit local shaping scheme for the shallow water equations, and the joint work between the South Carolina and the Florida state. Please go ahead. Look, next page. Okay, so first one, we're talking about the shallow water equation and the tri schemes. Then we present the details for the local time staging schemes. Our idea is to use the strong stability preserving Longo-Kutta scheme, and then we add some prediction, the correction strategy to the local time staging schemes. Then we show some numerical tests to demonstrate the efficiency and the parallel scalability of our LTS schemes. Next step. Okay, so right now in the MPath ocean, so use the Longo-Kutta, especially Longo-Kutta 4, is naturally parallel and simply to implement. But the biggest problem is the global CFL condition, controlled by the local mesh size. So here we try to develop a local time staging scheme. That's meaning we use spatially dependent time step size across the whole regions. It's still explicit, so easy to parallel, and for load balance, easier to do. But at the same time, we want the local time step scheme has the global conservation, like for example, exact conservation of the mass and the potential vorticity. At the same time, we want to maintain the high order accuracy of the schemes. Next. So the model equations are the shallow water equations. You can see in the Todd JCP paper and other papers. Here, the H is the fluid thickness, and the U is the velocity and the other things. Okay. Next page. The idea is the tree schemes for spatial degradation, in fact, is just a secret study. Okay, here use the Voronoi grid, and it's the dual is called the denominator triangulations. So put the fluid thickness in the center of the Voronoi cell, and put the Q potential vorticity, okay, mean vorticity on the corner of the Voronoi cell, and put the normal component of the velocity on the cell on the edge of the Voronoi cells, then apply the finite volume deteriorations. Next page. So here you can see from the continuous system, we can get a corresponding discrete system by applying the finite volume scheme. Here the H, you have to do the discrete finite volume operator on the center of the Voronoi cell, and the velocity, the U on the edge of the Voronoi cell. So sometimes you need some kind of like a reconstruction operators and so on. Okay, here always skip all the details and look at for the TRISC papers. Next page. Now we designed a local time staging schemes. We decide to use the SSP-RK called strong stability preserving RK instead of the regular Longo-Kutta 4 and so on. This because the SSP-RK is a linear convex combination of first order forward Euler schemes, so that we can easily apply the prediction and the correction schemes. Here, the first order SSP-RK is just forward Euler. SSP-RK2 is you just step from Tn to Tn plus 1, use the forward Euler. Then from Tn to Tn plus 2, another forward Euler. You take average, you get the second order accuracy at time Tn plus 1. And the SSP-RK is three similar things. So these three are called the optimal SSP-RKs. Okay, thank you. Next page. And we use apply a local time staging. That is, for example, see the left corner, the one-dimensional illustration. So the red part, we have a coarse time step size, and the blue part, we want to fine time step size. So two different regions with different time steps. The problem is you want on the interface, you want to advance on the fine time step size regions. You need all the values on the interface. Otherwise, you cannot go advance the time. So we need predict the values on the interface so that the fine time step size region can go ahead. At the same time, the coarse time step size region can do that too. On the right-hand side is two-dimensional local time staging. Here we have the purple and the pink regions. This is because the tree schemes use started variables. We have to design the interface correspondingly. Here we find to conserve mass exactly and the potential vorticity, we need 2-layer interfaces. That's why the pink and the purple regions. So our idea is the predictor character type. We do the SSP-RK scheme and the Taylor expansion to predict the interface values. Then we make the coarse region and the fine region advance in parallel. Then finally go back, we update the interface. Go ahead. So here is how to design the predictor, predict the value on the interface. We have to starting with the SSP-RK2 itself. Then we do the Taylor expansion. We use the information from SSP-RK with coarse time steps. We get all the interpolating values to guarantee the second order accuracy in time. Okay, go ahead. So then we design the second order LTS, local time stepping schemes. Here is a basic idea. First one, we just take the coarse time step size, go ahead, one step. Then we do the interface projection, all the values for the interface prediction. Okay, next page. Then we can advancing totally in parallel in the coarse region and the fine regions because they are separate. It's just like a general global explicit time steppings. So it's complete parallel. Next stage. Then we do the interface correction. Interface correction is used to guarantee the conservation property like the mass and the potential vorticity. So here we have to carefully design what flux used in the previous step. Now in the final, we have to put it back on the interface. That's the basic ideas. For details, we can see the formulas. Next page. Similarly, we can do the local time stepping with SSP-RK3. So we have to design the predictor for third order accuracies. There are 3 stages. So you need the predicted values for VNK, VNK plus 1 bar, and the VNK plus half, and so on. Next stage, next page. And same things, interface prediction, next page. And we advancing from Tn to Tn plus 1 on both coarse and the fine step size regions, completely in parallel. Then we do the interface correction. Next page. And next page. Then here we can theoretically prove the exact conservation of the mass and the potential vorticity, also conservation of the total energy within time truncation error. Also want to remark, our LTS with SSP-RK2 is a TVD, but our LTS with SSP-RK3 does not exactly conserve the TVD property, but we can prove it's TVD bounded. Okay, we have implemented everything in parallel. Okay, next page. And we show the 2D SOMA case. Everyone knows in the blue region with small time step size, in the purple region with large time step size. The time step size ratio is M. Okay, so next page. And we use the second order LTS scheme. First verify the accuracy. You can see all the second orders. The benchmark solution is RK4 with very small time step size. Okay, next step, next page. And we can verify the third order LTS scheme. The accuracy, exact as what we expected. Next page. And we also verify the mass conservation. Look at the bottom line. The left one is mass conservation. The right one is the potential vorticity conservation. Is up to the machine errors. The top is the energy. We can show the RK2, SSP-RK2 is not absolutely stable, but RK3, SSP-RK3 with LTS is still absolutely stable. And you see the energy is never blow up. Okay, next page. So we verify the shallow water test case 5. Here is the mounting area, the green and the red. There's initial velocity is not zero, it's rotating waters. And we get the blue region, the right one, blue region, we use smaller time step size and a smaller mesh size. Okay, and next step. And we verify, for example, you use a fixed step size ratio, use small time step size, you get expected convergence order. Also, you fix the cost times step size, use smaller and smaller fun time step size. You can see the error is decreasing. Especially when m equals 4, we find there's no need to go further because error decrease, but it's so small, almost keep constant. Next page. So that's 15 days, the simulation. We get a very consistent result as the taught papers. Okay, next page. And we'll also verify the exact conservation of the mass and the potential vorticity. And the energy, you see, the energy is a little deceptive. And the relative change is 10 to the negative 9. Okay. Next page. We also verify the parallel scalability. We use up to 128 processors. Of course, along the problem size increase, you get better load balance and the parallel scalability. You even get a super linear speed ups. So this LTS inherit the natural parallelism of the explicit schemes. Next page. Okay, it's done. Thank you. That's it.
All right, thanks, Lili. Any quick questions while I switch to the next talk?
Can you say a little bit about load balancing? It seems like the coarse region is going to, or the slow time step region is going to finish and just sit idle while the
very good question. In fact, we use weighted matrix algorithm because your mesh domatic position depends the weight. Weight is used is the mesh times ratio. M is bigger than your domain. The mesh size mesh number of nodes will be smaller, so that the total computation is uniformly distributed. So we use a weighted matrix to do the domatic computation.
Okay, thanks.